Assalamualaikum and a very good morning to Madam Munya and also my fellow friends. My name is Alia Sabrina 300577 and we are from Group 5. We'll be presenting on a classic problem on algorithm design, which is the 0-1 knapsack problem. So this is specifically to compare two popular solutions, which is the brute force and also the dynamic programming. So in this video, my friends and I will explore how the brute force approach works by trying all the possible item combination and how the dynamic programming provides a more efficient solution by breaking the problem into smaller overlapping problems.
Hi, my name is RUSHDINA HANIM and I will begin our presentation by introducing the 0-1 knapsack problem. In this problem, we are given a set of items, each with weight and value, and we are asked to determine the best combination of this item to maximize the total value without exceeding the fixed weight limit. The 0-1 part means each item must be either fully included in the selection or completely excluded, which there is no splitting of items. This type of binary decision making leads to exponential complexity, making it what we call an NP-hard problem. In simple terms, NP-hard problems are the problems that are difficult to solve efficiently. As the number of items increases, the time it takes to find the best solution grows extremely fast, often beyond practical limits. To help illustrate this, imagine a hiker preparing for a multi-day mountain trip. The backpack can only hold 10 kg and the hiker has 6 items to choose from, including a tent, sleeping bag, food, water, a first aid kit, and a jacket, each with different weights and usefulness. The hiker can't carry everything, so the goal is to select the best combination of items that provides the most benefit while staying within the weight limit. This example helps us to clearly understand how value versus constraint decision form the core of 0-1 knapsack problem. While this may seem like a high-gain problem, it's actually a powerful model used across various industries. In logistics and transportation, for instance, it helps in selecting the most valuable goods to load onto trucks or containers where space and weight are limited. In financial investment, it used to build optimal portfolios, choosing which asset to invest in within the limited budget to get the best possible returns. In cloud computing, this problem model the task of assigning jobs to limit computing resources like CPU or memory, trying to maximize the performance. And in emergency response planning, it helps agencies pack critical supplies into limited vehicles to maximize support delivery to disaster zones. So, as we can see, the 0-1 knapsack problem is not just theoretical. It's a fundamental problem that teaches how to make efficient and valuable choice under constraint. This is why we choose it for our project and to compare two algorithmic approach, brute force and dynamic programming.
Assalamualaikum. My name is FASIHAH BINTI NURSYAHIRAH, metric number 300661, and I'll be explaining how we solve the 0-1 knapsack problem using the brute force approach. So, what is brute force? The brute force algorithm is a simple but powerful method that tries every possible combination of items to find the one with the highest total value without exceeding the weight limit. Since each item can only be included, which is 1, or excluded, which is 0. So for now, we have 6 items. So we have 2 to the power of 6 equal to 64 combinations. Brute force is guaranteed to find the best answer, but it becomes very slow and inefficient when there are many items because it has to check everything. So, however, not all 64 combinations are useful. Some are invalid because the total weight is more than 10 kilograms, so they are automatically rejected. The rest are valid combinations where the total weight is less or equal to 10 kilograms. Out of this, we choose the one with the highest value. So here, if you can see, this is the table of the top 5 valid combination, which is the total value and the weight is among the highest. So the first one is food supply, first aid kit, sleeping bag, which is the total weight is 10 kg and the total value is 18. The second one, first aid kit and 10, the total weight is 9, and also the total value is 16. The third one is food supply and first aid kit. The total weight is 5 kilogram, and the total value is 14. The sleeping bag is the fourth one is sleeping bag and food supply. 4 plus 5 equal to 9 kilogram. The total value is 12, and the fifth one is first aid kit and the water bottle. The total weight is 10 kilogram and the total value is 12. The best solution is basically the first one, which gives the highest value without exceeding the 10 kilogram limit. So I can see the selected item is food supply and first aid kit. The total weight is 10 kilogram and the total value is 27. In summary, brute force is a simple but time-consuming method. It's good for small problems like ours. However, it's not suitable for larger data sets due to its exponential time complexity.
Okay, next we focus on dynamic programming approach. Dynamic programming is a method to solve big problems by breaking them into smaller problems. Once we solve a small problem, we save the result so we don't have to do the same work again. This helps us solve problem faster and more efficiently. Okay, next, this is a final result for the dynamic programming table. At every step, we make a decision. First decision, we don't take the item. We use the value from the row above. As you can see the formula, dpiw equals to dpi minus 1 and w. For example, for the dp1 and 5, the value is 4. Okay, next, for the dp2 and 5, we decide to use the value from the row above. So we use the formula dpi equals to 1 w. So it becomes dp 2 minus 1 and w is 5. The result will be dp 1 and 5. So that's why the value become same 4 and 4. For the second item, we will take the item if it fits. Means if the total weight is not excess the bag capacity, which is 10 kg, we take the item. We add its value to what we could carry with the remaining weight. It is the formula for the take the item. Next, this is how we make the dynamic programming table. For the first row and column are 0 because no items or weight are equal to 0 value. As we go row by row, if the item weight is more than the current column capacity, we will copy the value from the above because the maximum capacity is only 10. If the item fits, we will compare taking it versus not taking it. For example, if we don't take the food supply, the value becomes only 4. But if we take the food supply, the value becomes 8. So we choose the bigger one, which is 8. So the value for DP3 and 5 will become 8. Okay, next, this is how we choose the item that we want to put in the bag. We start at the bottom right cell, which is DP6 and 10. Then we compare with the cell above. For the value DP6 and 10 is 18. If the total value with the cell above is same, which is 18 and 18, we will not pick the item. But if different, we will pick the item. For example, for DP5 and 10, we compare with DP4 and 10. The value is different, which is 18 and 12. Then we will subtract the item weight and move up. Repeat until the weight becomes 0. Based on backchecking, the item that we choose is sleeping bag, which is 5 kg and the value is 4. Next, food supply, 4 kg and the value is 8. And last, first aid kit, 1 kg and the value is 6. The total weight becomes 10 kg and total value is 18. This is the best combo we can get with 10 kg.
For pseudocode comparison, this slide shows the side-by-side pseudocode for solving the 0-1 knapsack problem using two different approaches, which are brute force and dynamic programming. On the left, the brute force algorithm uses recursion to evaluate every possible subset of items. It either includes or excludes each item and explores all combinations until the best total value is found. Although this guarantees the correct results, it becomes inefficient as the number of items increases. On the right, we have the dynamic programming solution. This approach builds a table, dpiw, to store the maximum value for each subproblem, that is, the best value for the first I items with capacity W. This method avoids redundant calculations by reusing previous results, making it significantly faster for larger input sizes. Now let's compare the efficiency of both algorithms in terms of time and space complexity.
The brute force algorithm has a time complexity of O 2 to the power of n because it explores all possible combinations of items. Its space usage is On mainly because the recursive function calls. On the other hand, the dynamic programming approach reduces the time complexity to O n times W, where n is the number of items and W is the knapsack capacity. This is much more scalable, however, it uses O n times W space to store the two-dimensional table. We can further improve the space usage in dynamic programming by using a 1D array instead of 2D table. This optimization brings the space complexity down to OW while keeping the time complexity the same. This is useful when working with larger capacities or when memory is limited.
Hi everyone, my name is NURSYAHIRAH BINTI SUKARDI 300646. In this section, I will explain the performance of the brute force and dynamic programming method in solving the 0-1 knapsack problem. So, the evaluation is based on time, complexity, scalability, and precision across different input size. First is small, 5 items. Next is medium, 10 items, and large is 20 and above. So the goal is to assess the practical feasibility of both algorithms. Next is performance comparison table. As you can see here, first column is number of items, which is 5, 10, and 20 and above. And then brute force result, time efficiency, dynamic programming result, and time efficiency for dynamic. Okay, for item, which is 5, as you can see here, for brute force result and dynamic programming result is same. And their time efficiency too is same, which is fast. And then for 10 item, brute force result and dynamic programming result is same too. But for time efficiency, for brute force result is slow, while time efficiency for dynamic is fast. And then for large set, which is 20 and above, for brute force and dynamic, which is we can see different, where brute force result is fails, which is they cannot do. And then but dynamic programming is still same. And then time efficiency, of course, for brute force extremely slow. And then for time efficiency, dynamic programming is stable. Okay, next we move to observation and summary part. Okay, first is for small data set, which is 5 items. For a small data set, which is 5 items, both brute force programming and dynamic programming perform equally same. The brute force approach here is feasible because the number of combinations is still manageable. Meanwhile, dynamic programming is also effective and introduce no additional overhead, proving that for a small input sizes, both methods are suitable. Next is medium dataset, which is 10 items. So here we start to see the difference, where the brute force algorithm begins to slow down significantly due to its exponential time complexity. That's O to n, while it still provides accurate result, but it's no longer efficient because it's slow. And then for dynamic programming, both speed and accuracy thanks to its more optimized time complexity, O and W, where n is the number of items and W is the capacity. Next is large dataset, which is 20 and above items. Here, brute force becomes highly impractical because the time required increases exponentially and may even cause the system to crash or fail. And then on the other hand, dynamic programming shows strong stability and consistently accurate result, making it ideal for solving large-scale problems efficiently. Okay, next is summary. So, programming outperforms brute force in terms of efficiency, scalability, and practical application. While brute force may be useful for validation in academic settings, and dynamic programming is more suitable for solving large-scale optimization problems due to its time and space efficiency. So, the conclusion is, this project highlights the importance of algorithm selection. Brute force is simple and true, but become inefficient as the problem size grows. Dynamic programming, however, offers a more efficient solution by using a bottom-up approach and storing intermediate results, which lowers both time and space complexity. So, these strengths make it highly applicable in areas such as logistics, finance, and resource planning, where performance matters the most.